Hey everybody, welcome to the next video lesson. Today we're going to talk about mass defect and what that means and what the implications are of mass defect to our natural world. Taking a look at this first sentence, after investigating nuclei of different elements, different isotopes, scientists observed that the mass of the nucleus is actually less than the sum of the protons and neutrons that make up the nucleus. Here's an example. Helium has a mass number of 4. That means it has 2 protons and 2 neutrons. If one proton is 1.00728, and scientists know the mass of a proton and neutron to this level of precision, then 2 times that is, well, this number, 2.01456. A neutron is slightly more massive than a proton at 1.00866 times 2 is this. So if you add these two numbers together, you get 4.03188 AMU. The actual mass of a helium isotope is 4.00150. There's a larger mass of the nucleons, which are the protons and neutrons, than the mass of the actual particle itself. This difference is 0.03038 AMU. But what does this mean? Well, it took a great mind like Albert Einstein to make the relationship between energy and matter. And the difference between the nucleons and the actual particle itself must be converted to energy in some way. And this is how he came up with his famous E equals mc squared formula. When a system, whether it be a chemical system or a nuclear system, gains or loses energy, it also gains or loses a quantity of mass. What that means is that if it gains or loses mass, it also gains or loses energy. The formula, which we already know, is E equals mc squared, where c is the speed of light, which is 3 times 10 to the 8th meters per second, m is the mass, and E is the change in energy. So if the energy change is negative, that must mean it loses mass, and if the energy change is positive, then must mean it gains mass. And in this case, since the nucleons were larger than the actual mass of the particles, then it lost mass, and that, as a result, the creation of the helium nucleus must release energy, which negative energy is exothermic energy. And if you remember that number from the last slide, 0.0308 or something, that's the amount of AMUs. The mass is really small, but when multiplied by the speed of light squared, well, this energy value becomes very big very quickly. And I'm going to show you an example of those calculations on the next slide. This difference between the nucleons and the actual particle itself is known as mass defect and can be used to calculate the energy needed to break apart a nucleus into its component parts. In other words, it can also be used to determine the stability of a nucleus. So here's that number that we calculated 2 slides ago. It's the mass defect of the helium nucleons versus the actual helium particle. 1 atomic mass unit is equal to 1.6605 times 10 to the negative 24th grams. Then you convert grams to kilograms. What you have is that mass defect in AMU, 5.0446 times 10 to the negative 29th kilograms. We'll put that in for m for mass and take the speed of light squared, and we get, in the units of joules, 4.5 times 10 to the negative 12th joules. Now that's per particle. But what happens if you have a mole of particles? Well, multiply this number by Avogadro's number, 6.02 times 10 to the 23rd, and you get a final answer of 2.73 times 10 to the 12th joules. That's how much energy it would take to break apart a mole of helium nuclei. But think about it the other way. That's how much energy is released when you just take protons and neutrons and create helium nuclei out of those particles. That is an incredible amount of energy, which is why you can justify the amount of energy released when fusion and fission, which are topics that we're going to be talking about here in a little bit, that's how we get those astronomical amount of values, such high amounts of energy released. This energy that we just calculated per particle or per mole is known as the nuclear binding energy. It's the energy required to decompose a nucleus into its components. Higher the value means the tighter the nucleus is held. That also means that the higher the value, the more energy released when that nucleus is broken. I grabbed this picture out of the book, which I think illustrates this point rather well. And I know I've talked about iron as an important element in the sense of nuclear chemistry, and we're going to get to that whole reason why today. Small elements increase their nuclear binding energy as they get bigger and bigger and bigger. So as these elements get bigger in mass, then it requires more energy to break apart those nuclei. So when they form, they release more energy, and when they are formed, it takes more energy to break them apart. This trend of increasing nuclear binding energy maxes out at iron 56. At that point, as you get bigger, the nuclear binding energy slowly starts to get smaller and smaller and smaller and smaller and trails off here until we get to the last naturally occurring element, uranium, over here. So when you're looking at this graph, the higher the value, the more stable the nucleus is. And the lower the value, the least stable the nucleus is. But imagine this is an energy graph. Oftentimes it's written in textbooks kind of inverted. So it starts high and goes low at iron and then comes up over here. In that case, that would be the energy released when these particular nuclei are created. But we write it like this in our textbook as the energy needed to break those nuclei. So if iron is the most stable nucleus of any naturally occurring nucleus on the periodic table, then anything smaller than that will want to achieve stability through fusion and combining of nuclei. In this case, it would release energy in order to do that. But on the opposite side of iron, if you were a really big nucleus, then your tendency is to try and get smaller, and you're going to go through fission or split up your nuclei in order to release energy to get to that point. Because the higher up on this graph you are, the more energy you needed to release in order to achieve that stability. So now I'm going to bring in a little bit of astronomy for you. So if small elements want to combine to become bigger elements because it's a more stable situation, then at the sun, inside the sun, it's a lot of hydrogen and hydrogen is combining to make helium, and then helium combines with other helium and hydrogen to make even larger elements and even larger elements and even larger elements. And at the center of the sun, although a very small amount, there is some iron at the middle because it's the most stable nucleus. Fusion will happen and create larger elements and larger elements and larger elements, but the largest element that can be created through fusion is iron because it's the most stable nucleus. Now, what about all those other elements that exist in the universe? We know they exist. Uranium, tin, lead, copper, gold, silver. All of these elements are up here. These are large isotopes that are unstable. They prefer to be like iron, and so they will go through fission in order to become smaller and achieve a more stable energy state. Well, how do those particles even come to exist? Well, at the death of a star, it supernovas and it spits all of its matter out into the far reaches of the galaxy. That is a very highly energetic and violent time of a star's life, and it crashes all of those particles together even more and even more and even more. And so at supernova, we can get larger and larger and larger nuclei created, and that's how we get things like gold and silver and lead. Those are the results of a supernova, but the actual burning of a star will create no more than iron. Anything else happens to be the result of a supernova that created those even larger particles, and once those particles are created, they're going to begin the long and slow process of nuclear fission until it reaches back to iron. Another thing to observe is that we know with very high certainty that the middle of the Earth is molten iron. It's liquid iron surrounded by solid iron, surrounded by that mantle, but all of that heat and pressure that creates that iron in the center core all comes from nuclear fusion of smaller elements creating iron and releasing energy, and all of that fission of larger elements splitting up and releasing energy. But all that iron falls to the middle and collects there, which is why we know that the center of the Earth is made of iron, some of it liquid, some of it solid. So to wrap it all up here, two conclusions can be drawn from the trend of the line of the last page graph. Light elements will gain more nuclear stability when they combine to create fusion, in the process releasing energy, and heavier elements will gain more stability by splitting up and also releasing energy. And so that is why we know that iron is the most stable nucleus, because it has the highest nuclear binding energy, and it's also why we know that it is the most abundant element at the center of our Earth and at the center of most stars. Coming up in the next video lesson, we'll talk about the specifics of fusion and fission and how we as humans can use them for our benefit. Well, that takes care of this video lesson. Thanks for watching.